Opening, the impossible challenge. In the steaming jungles of the South Pacific, during the darkest days of World War II, American military commanders faced an impossible engineering challenge. They needed to build airfields capable of supporting heavy bombers and fighters, and they needed to build them fast, not in months, not in weeks, but in days. Traditional concrete runways required massive amounts of materials, heavy equipment, months of construction time, and stable supply lines. In the island-hopping campaigns across the Pacific, none of these luxuries existed. Engineers were expected to carve functional airstrips out of dense jungle, swampy terrain, and coral islands, where even walking was treacherous. The solution to this seemingly impossible problem would come from an unlikely source: a small team of engineers working in an experimental laboratory in North Carolina, led by a determined military engineer who understood that winning the war in the Pacific would require revolutionizing how airfields were built. The year was 1941, and America was not yet officially at war, but military planners could see the storm clouds gathering. The existing methods of airfield construction were wholly inadequate for the kind of mobile, rapid deployment warfare that would characterize modern conflict. When engineers did attempt to build temporary airfields, they used whatever materials were locally available: crushed coral, compacted earth, gravel, or pierced steel planking that was heavy, difficult to transport, and prone to warping under tropical heat. These makeshift runways quickly deteriorated under the weight and stress of repeated aircraft landings and takeoffs, especially during monsoon seasons when rain turned dirt strips into impassable mud. Aircraft would bog down, landing gear would sink, and entire air operations would grind to a halt. Commanders needed runways that could be transported in sections, assembled quickly by troops with minimal equipment, and withstand the punishing conditions of tropical warfare. The solution would come to be known as Marston Mat, and it would transform military engineering forever. The birth of an idea: engineering under pressure. The story of Marston Mat begins at a remote facility in North Carolina called Camp McCall. Though the initial research and development actually took place at an even more obscure location, the small town of Marston, North Carolina. It was here that the U.S. Army Corps of Engineers established a testing ground specifically dedicated to solving the airfield construction problem. The lead engineer on the project was a man whose name has largely been forgotten by history, but whose contribution to the Allied victory in the Pacific cannot be overstated. Working under intense pressure and with limited resources, this team of military and civilian engineers set out to design a portable runway system that could meet a seemingly contradictory set of requirements. The specifications were daunting. The runway material had to be strong enough to support aircraft weighing up to 30,000 pounds or more, including fully loaded bombers like the B-25 Mitchell and eventually even heavier aircraft. It had to be light enough that individual sections could be carried and assembled by small teams of soldiers without heavy machinery. It had to interlock securely so that sections wouldn't shift or separate under stress, yet the connection had to be simple enough that troops could assemble it quickly in combat conditions, possibly under enemy fire. The material had to resist corrosion in saltwater environments, withstand baking tropical heat without warping or buckling, and not become slippery when wet or covered in morning dew. It needed to drain water effectively to prevent flooding and pooling. Most ambitiously, it had to be manufacturable in enormous quantities using materials and industrial capacity that wouldn't compete with other critical wartime production needs like ships, tanks, and artillery. The engineering team began by studying all existing portable runway systems. The British had developed various forms of pierced steel planking, but these systems were heavy, cumbersome, and prone to maintenance issues. Some experimental systems used wood, but wood rotted quickly in tropical humidity and couldn't bear the weight of increasingly heavy aircraft. Aluminum was too scarce and too valuable for other applications. The engineers kept coming back to steel, but not conventional solid steel plates. Those would be impossibly heavy. They needed a design that maximized strength while minimizing weight,
And the solution lay in the principle that engineers had been using in other applications for years, the perforated plate. By creating a pattern of holes in the steel, engineers could reduce weight dramatically while maintaining most of the material's structural strength. But the pattern of holes wasn't arbitrary. It had to be carefully calculated. Make the holes too large, and the mat would be too weak or would trap landing gear wheels. Make them too small, and the weight savings would be negligible. The shape of the holes mattered too. Round holes were easy to manufacture, but didn't provide optimal strength characteristics. The team experimented with various shapes, rectangles, triangles, hexagons, and eventually settled on a distinctive pattern that would become the visual signature of Marston mat: rows of elongated holes with reinforced edges, arranged in a precise geometric pattern that distributed loads effectively.
The design evolution from concept to reality. The first prototypes were disasters. Early test sections buckled under weight, connections failed, and the steel warped in simulated tropical conditions. Each failure provided data, and the engineers refined their design through countless iterations. They discovered that the thickness of the steel was critical. Too thin, and it would bend permanently under load. Too thick, and it became too heavy to handle efficiently. They settled on a gauge that balanced these competing demands, but they also learned that the steel had to be specially treated. Standard steel would rust within weeks in the salt spray environment of Pacific Islands. The team worked with metallurgists to develop coating and treatment processes that would provide corrosion resistance without adding significant weight or cost. The interlocking mechanism went through dozens of designs. The engineers knew from studying battlefield conditions that assembly crews would be working in mud, rain, darkness, and often under the stress of enemy attack or imminent aircraft arrival. The connection system had to work even when sections were slightly misaligned or when debris was present. They eventually developed a hook and slot system on the long edges of each mat section with overlapping flanges that could be dropped into place and then locked by inserting a simple connector bar. The short ends of the mats featured a different connection system that allowed for slight angular adjustments, crucial when laying mats over uneven terrain. Each mat section measured 10 feet long by 15 inches wide, a dimension chosen very deliberately. This size was large enough to cover ground quickly. A crew could lay significant runway length in a day, but small enough that 2 soldiers could carry and position each section. At approximately 70 pounds per section, the mats were at the absolute upper limit of what could be handled manually for extended periods, but this weight was necessary to provide adequate strength. The engineers calculated that a standard runway required approximately 1,800 sections per 1,000 feet of length, depending on the width desired. A typical fighter strip might be 100 feet wide and 3,000 feet long, requiring well over 30,000 individual mat sections. But the design wasn't just about the individual mats, it was about the complete system. The engineers designed specialized edge sections that would frame the runway and prevent mats from sliding outward. They created taxiway sections with slightly different hole patterns optimized for slower-moving aircraft and tighter turns. They developed hard stand sections for parking areas where aircraft would sit for extended periods with their full weight concentrated on landing gear. Each component had to work with all the others to create a complete, functional airfield system. The team even designed specialized tools for the assembly crews: bars for aligning sections, mallets with specific head shapes for driving connector pins, and extraction tools for removing damaged sections.
Testing, simulating hell on Earth. With prototypes in hand, the testing phase began in earnest, and it was brutal. The engineers needed to simulate every conceivable condition that airfields would face in the Pacific theater, and then push those conditions beyond expected limits to ensure adequate safety margins. At the test facility in North Carolina, they constructed sample runway sections on various terrain types. They built test strips on soft clay soil that simulated soggy jungle conditions. They created coral-based substrates that mimicked the makeup of Pacific atolls. They even trucked in sand to simulate beach landing scenarios where airfields might need to be established on or near shorelines. Then they punished these test sections mercilessly. They drove trucks loaded with ballast to simulate aircraft weight, running them repeatedly over the same sections to test durability under repeated stress cycles. They brought in actual aircraft, whatever could be spared from training operations, and conducted hundreds of landings and takeoffs, carefully monitoring the mats for any sign of failure, deformation, or connection weakness. Engineers crawled across the test sections with measuring instruments after each test run, checking for minute changes in elevation, detecting any bending or warping, and examining connections for loosening or stress damage. The weather testing was particularly crucial and particularly challenging. In North Carolina, they couldn't perfectly replicate tropical monsoons or the salt spray environment of Pacific Islands, but they did their best. They installed fire hoses and sprinkler systems to drench the test runways, then immediately ran aircraft over them to see how the wet surfaces performed. They were looking for drainage characteristics. Water had to flow through the perforations and away from the runway surface quickly to prevent hydroplaning and loss of traction. They also tested freeze-thaw cycles, recognizing that some Pacific islands had surprisingly cold nights, and that the Marston mat system might also be used in European or North African theaters where temperature extremes were more pronounced. One critical test involved deliberately damaging sections mid-runway and timing how quickly a repair crew could remove the damaged section and replace it with a fresh mat. This test revealed an unexpected advantage of the modular system. Unlike concrete runways, where damage meant extensive repairs and long downtimes, a damaged Marston mat section could be swapped out in minutes, and the runway could return to operation almost immediately. This repairability would prove crucial in combat, where bomb damage and combat stress regularly damaged airfield surfaces. The engineers also tested failure modes. They wanted to know exactly how the system would fail when pushed beyond its limits, so they could recognize warning signs and prevent catastrophic failures. They deliberately overloaded sections until they buckled, studying the deformation patterns. They stressed connections until they broke, examining the fracture characteristics. They exposed test sections to extreme heat using portable heating equipment, watching how the steel expanded and whether the thermal expansion would cause buckling or connection failure. Every test generated data, and every piece of data informed refinements to the design.
Manufacturing, the industrial challenge. Once the design was finalized and tested, an entirely new challenge emerged: manufacturing millions of mat sections rapidly enough to meet military demand. In 1942, American industry was in the midst of a massive conversion from peacetime to wartime production. Factories that had produced automobiles were retooling to build tanks and aircraft. Steel mills were running at capacity to meet demand for ships and artillery. Into this already stressed industrial ecosystem, the War Department now had to inject a massive new requirement for a product that didn't exist just months earlier. The manufacture of Marston mat required specialized equipment. The steel had to be cut to precise dimensions, then the hole pattern had to be punched or drilled with exacting accuracy. The edges had to be formed to create the interlocking features, and this forming process had to maintain tight tolerances. If the hooks and slots didn't align perfectly, assembly in the field would be difficult or impossible. Finally, each mat had to go through the anti-corrosion treatment process, then be inspected, bundled, and prepared for shipping. The entire production line had to be designed from scratch. The War Department contracted with multiple manufacturers across the United States, hoping to distribute the production load and create redundancy in case any single facility was damaged or destroyed. steel mills in Pennsylvania, fabrication plants in Ohio and Illinois, and specialized manufacturing facilities in California all received orders for Marston mat production. The government provided the final specifications, and manufacturers were required to meet exacting quality standards. Every mat had to be interchangeable with every other mat, regardless of which factory produced it. This interoperability was crucial because airfield construction crews in the field would be working with mats from multiple production runs and multiple manufacturers, all mixed together. The manufacturing process began with sheets of steel rolled to the specified gauge. These sheets moved to cutting stations where they were sheared to the 10-foot by 15-inch dimension. The sheets then proceeded to massive punch presses where the hole pattern was stamped out. These presses required tremendous force to punch through the steel cleanly, and the tooling had to be maintained meticulously to ensure that every hole was positioned accurately and that the edges were clean and free of burrs that could create stress concentration points. The distinctive hole pattern meant that the punch presses were custom designed for this specific purpose. They couldn't easily be retooled for other products, representing a significant commitment of industrial capacity. After punching, the mats moved to forming stations where the long edges were bent to create the interlocking hooks and slots. This forming operation was particularly tricky because the steel had to be bent without cracking or creating weak points along the bend lines. The short ends received their own specialized edge treatments. Then came the corrosion treatment, which varied by manufacturer, but typically involved hot-dip galvanizing or application of specialized paint and coating systems. The treated mats then went through quality control, where inspectors checked dimensions, hole patterns, edge formation, and coating quality. Mats that didn't meet specifications were rejected and sent back for rework or scrapping. Approved mats were bundled in stacks of specific quantities, banded together with steel straps, and prepared for shipment. The packaging had to protect the mats during transport. They would travel by rail across the United States to ports, then by ship across thousands of miles of ocean, sometimes sitting in the holds of cargo vessels for weeks or months. The protective packaging also had to be quickly removable once the mats reached their destination, because construction crews in the field would be working with mats from multiple production runs and multiple manufacturers, all mixed together. By the end of 1942, American industry was producing Marston mat at a rate of millions of square feet per month. The scale of production was staggering. By some estimates, the total production of Marston mat and its variants during World War II exceeded 2 billion square feet, enough to build nearly 800 miles of runway if laid end to end. This represented hundreds of thousands of tons of steel, countless hours of labor, and a significant portion of America's industrial output during the war years. The production of Marston mat competed directly with other critical steel needs, and the fact that military planners continued to allocate resources to mat production throughout the war speaks to how essential it became to military operations.
Deployment, getting mats to the front lines. Manufacturing the mats was only half the battle. Getting them to where they were needed presented its own formidable logistics challenge. In the European theater, supply lines were relatively short and well established. Materials could move by rail across Britain to airfields under construction, or could be trucked from port facilities to nearby construction sites. But in the Pacific, the logistics situation was vastly more complex and difficult. Pacific islands often had no port facilities at all. Ships had to anchor offshore and transfer cargo to landing craft, which would then ferry the materials to beaches. The Marston mat sections, bundled and banded, had to be offloaded from cargo ships, lowered into landing craft, transported through surf and across beaches, and then moved inland to construction sites. Every step of this process was physically demanding, time-consuming, and dangerous. It often occurred within range of enemy artillery or air attack. The weight of the mat sections made handling difficult. A typical bundle contained multiple mats and weighed several hundred pounds, requiring teams of soldiers or dock workers to move it.
Specialized cargo handling equipment like cranes and forklifts were often unavailable on remote islands, so much of the moving was done with simple tools: crowbars, rollers, ramps, and muscle power. The U.S. Navy's Seabees, the construction battalions, became specialists in Marston mat deployment. These were the men who would actually build the airfields, and they developed techniques and procedures through hard-won experience. They learned to organize their mat stockpiles efficiently, keeping different components separated so crews could quickly access what they needed. They developed their own loading and unloading methods that were faster than standard procedures. They created improvised transport systems using logs as rollers to move heavy bundles across soft ground. The Seabees took pride in their speed and efficiency, and units competed to see who could construct airfields fastest. Transport from ship to construction site often required building temporary roads or paths, which themselves required construction effort. In many cases, the first use of Marston mat on an island wasn't for the airfield itself, but for creating temporary roads so that construction equipment and supplies could reach the airfield site. Once the initial access routes were established, the serious work could begin.
Construction: building an airfield in 2 days. The construction of a Marston mat airfield was a carefully choreographed operation that had been refined through experience and training. The Seabees and Army engineers who performed this work had practiced the procedures repeatedly, and they executed them with remarkable efficiency. The process began long before the first mat section was laid. It started with site preparation, and this was often the most time-consuming and difficult part of the entire project. The first step was clearing the construction site. In jungle environments, this meant removing trees, brush, and vegetation across the entire area where the airfield would be built. This wasn't simple mowing. Jungle trees could be massive, with root systems that had to be extracted completely. Crews used bulldozers when available, hand saws and axes when they weren't. The cleared vegetation had to be moved away from the construction site, because it would rot and create soft spots if left buried under the runway. Clearing a typical fighter strip site, roughly 300 feet wide and 3,000 feet long, could take days or even weeks, depending on the density of vegetation and the equipment available. Once cleared, the ground had to be leveled and graded. The Marston mat system could accommodate some unevenness, but major irregularities would create stress concentrations that could lead to mat failure. Grading crews used bulldozers and road graders to create a relatively flat, even surface with proper drainage characteristics. The runway had to crown slightly in the center, so water would drain to the sides rather than pooling in the middle. Drainage ditches were dug along the runway edges to carry water away. In swampy areas, crews sometimes had to build up the entire runway site by bringing in fill material, coral, crushed rock, or compacted soil, to raise the surface above the surrounding terrain and ensure adequate drainage. The prepared surface then received a base layer. In some locations, this was compacted coral. Many Pacific islands were essentially coral formations, and crushed coral, when compacted, provided a reasonably stable base. In other locations, crushed rock or gravel served as the base layer. The critical requirement was that the base be well drained and firm enough to support the weight of both the mats and the aircraft that would use them. A soft or unstable base would allow mats to sink unevenly, creating a bumpy runway surface that would stress aircraft landing gear and could even lead to crashes. With the site prepared, the actual mat laying could begin, and this was where the system's design brilliance became apparent. A crew of experienced Seabees could lay mat sections at an astonishing rate once they got into rhythm. The process started at one end of the runway and progressed systematically. The first row of mats was carefully aligned and positioned, often with the help of survey equipment and string lines to ensure straightness. These initial mats were critical because every subsequent row would reference off them. Any error in the first row would propagate down the entire runway length. Working in teams, soldiers would position mat sections and lock them together. One team member would align the mat, while others worked the locking mechanism, inserting connector bars and ensuring that the hooks properly engaged the slots. The work required coordination and timing. If one end of a mat was locked before the other end was properly aligned, the misalignment would stress the connections and make it difficult to position adjacent mats correctly. Experienced crews developed a rhythm, almost like a dance, where each team member knew exactly what to do and when to do it. As each row was completed, the next row began immediately. The mats overlapped slightly along the long edges, providing extra strength and preventing gaps from opening up. The crews worked their way down the runway length, row after row, the rectangular pattern of the mats creating a distinctive appearance that became iconic in photographs of Pacific airfields. Corner sections and edge pieces required special attention because they had different connection mechanisms and had to be positioned precisely to frame the runway properly. A well-trained and experienced CB battalion could lay thousands of square feet of mat per day. Contemporary accounts describe instances where crews laid complete fighter strips, 3,000 feet long and 100 feet wide, in as little as 48 hours, though this was under ideal conditions, with experienced crews, good weather, and adequate supplies. More typically, a complete airfield, including taxiways, hard stands, and support facilities, might take 4 to 5 days. Even this was remarkably fast compared to traditional construction methods. A concrete runway of similar dimensions would take months to complete, assuming all the necessary materials and equipment were available. The crews worked in shifts, often around the clock, because getting the airfield operational as quickly as possible was crucial. In many cases, enemy forces were nearby and could attack the construction site. Speed meant survival. The sooner the airfield was complete, the sooner friendly aircraft could begin using it for protection and offensive operations. There are numerous accounts of airfields being completed just in time, with the first aircraft landing while construction crews were still working on taxiways or parking areas.
The science of the surface. Understanding load distribution. To truly appreciate the engineering achievement that Marston mat represented, it's necessary to understand the physics and engineering principles that made it work. When an aircraft lands, it doesn't simply rest on the runway, it impacts with tremendous force. A fighter aircraft weighing 15,000 pounds might land at speeds exceeding 100 miles per hour. Even with shock-absorbing landing gear, that impact translates to enormous stress on the runway surface. The runway must absorb and distribute this force without failing, deforming, or becoming damaged. Traditional concrete runways handle these forces through sheer mass and compressive strength. Concrete is extremely strong in compression, and a thick concrete slab distributes loads across a large area into the underlying soil. But concrete is also brittle. It cracks when subjected to tensile stress or impact, and repairing cracked concrete is difficult and time-consuming. Steel, by contrast, is strong in both compression and tension and has much better impact resistance. The challenge is using steel efficiently. A solid steel plate thick enough to support aircraft would be impossibly heavy. The Marston mat design solved this through several clever engineering principles working together. First, the perforated pattern reduced weight while maintaining strength by keeping material where it was structurally necessary and removing it where it wasn't. The steel around the holes acted like a network of beams, distributing loads throughout the structure. When weight pressed down on one part of a mat, the forces spread through these beam-like structures to adjacent areas and ultimately to the supporting ground beneath. The whole pattern was optimized through extensive testing and calculation. The engineers had to ensure that the holes were small enough that aircraft wheels wouldn't sink into them or catch on edges, but large enough to provide significant weight savings. The elongated shape of the holes had advantages over circular holes. It provided better structural characteristics in the longitudinal direction, which was the primary direction of stress as aircraft rolled down the runway. The interlocking system was crucial to load distribution.
Individual mats weren't designed to carry loads independently. The system worked because mats were connected together into a continuous surface that acted almost like a single large plate. When weight pressed on one mat, the connections transmitted some of that force to adjacent mats, spreading the load over a wider area. This load sharing was essential because it meant that even a very heavy aircraft, with its weight concentrated on relatively small landing gear footprints, would still distribute forces over dozens of mat sections. The flexibility of the system was also beneficial. Unlike rigid concrete, Marston mat could flex slightly under load. This flexibility allowed the runway to conform somewhat to minor irregularities in the underlying terrain without breaking. The mats could handle differential settlement. If one area of the runway sunk slightly due to soft soil beneath, adjacent mats would flex to bridge the difference rather than cracking or breaking. This flexibility also helped absorb impact forces during landings, reducing peak stresses. The drainage holes served an aeronautical purpose beyond just water removal. In wet conditions, a smooth runway surface can develop a thin layer of water that leads to hydroplaning, where aircraft tires lose contact with the surface and skid uncontrollably. The perforations in Marston mat provided pathways for water to escape immediately, maintaining better tire-to-surface contact even in heavy rain. The holes also provided some aerodynamic benefit by reducing crosswind effects on parked or taxiing aircraft. Engineers had to consider thermal effects as well. Steel expands when heated and contracts when cooled, and in tropical environments, the temperature difference between early morning and midday could be substantial. The mat system had to accommodate this thermal expansion without buckling or creating gaps. The connection system provided just enough freedom of movement to allow for thermal expansion while still keeping mats securely locked together.
Combat experience proving the concept under fire. The true test of any military technology comes in combat, and Marston mat faced this test throughout the Pacific Theater from 1942 through the end of the war. The first major deployment was in the Solomon Islands campaign, where American forces needed to rapidly establish air bases to support operations against Japanese-held islands. The conditions were exactly what the engineers had tried to simulate in testing: dense jungle, heavy rainfall, coral soil, and the constant threat of enemy attack. At Guadalcanal, Seabees constructed Henderson Field using Marston mat, and this airfield became a crucial base for American air operations in the South Pacific. The construction occurred under incredibly difficult conditions. Japanese forces were still present on the island, supplies were limited, and tropical diseases ravaged the construction crews. Despite these challenges, the airfield was completed rapidly enough to become operational while fighting was still ongoing. The aircraft operating from Henderson Field proved decisive in the Guadalcanal campaign, providing air support for ground troops and interdicting Japanese supply efforts. Henderson Field also provided the first real-world test of Marston mat's durability and maintainability. The airfield took regular enemy fire from artillery, aircraft bombs, and naval bombardment. Sections of the runway were frequently damaged, creating craters and destroying mats. The repair crews, working often at night or between air raids, would remove damaged sections, level the crater, and install fresh mats. The speed of these repairs, sometimes measured in hours rather than days, allowed the airfield to remain operational even under sustained attack. This repairability proved to be one of Marston mat's most valuable characteristics in combat. As the island-hopping campaign progressed, Marston mat airfields appeared across the Pacific. At Tarawa, Kwajalein, Saipan, Tinian, and dozens of other islands, Seabee battalions constructed temporary airfields that would serve as stepping stones for the advance toward Japan. Each installation taught new lessons about construction techniques, maintenance procedures, and operational use. The Seabees developed new methods for dealing with specific terrain types. They learned that coral bases worked better in some locations, while compacted earth was preferable in others. They developed techniques for repairing mats in situ when replacement wasn't immediately possible. The system's modularity proved advantageous in unexpected ways.
When operations moved forward and an airfield was no longer needed, the Marston mats could be recovered, bundled, and shipped to the next location. While this rarely happened due to the logistical challenges and the rapid pace of operations, it meant that mats weren't necessarily single-use items. Some mat sections saw use at multiple airfields as the campaign progressed. Aircraft crews adapted to the characteristics of Marston mat runways. The perforated surface provided good traction in most conditions, though landing on mats in heavy rain was initially unnerving for pilots accustomed to concrete or packed earth. The distinctive sound of aircraft tires rolling over the perforations became familiar to anyone who spent time around Pacific airfields. Pilots learned that the mats were more forgiving of rough landings than concrete. The slight flexibility of the surface absorbed some impact energy that concrete would have transmitted directly to the aircraft's structure. There were challenges and limitations that combat experience revealed. In areas with very soft soil, additional foundation work was sometimes necessary to prevent mats from sinking unevenly. Heavy aircraft operating in wet conditions could sometimes displace mats near the runway ends where braking forces were highest. Engineers developed additional securing methods, including stakes driven through holes in the mats into the ground beneath, to address this issue in problematic locations. The mats also had to withstand conditions that hadn't been fully anticipated during testing. The heat from jet exhausts when aircraft engines were run up to full power could damage mats near parking areas. This led to the development of specialized heat-resistant sections for use in these high-temperature zones. Salt corrosion proved more aggressive than anticipated in some locations, particularly where mats were frequently covered by sea spray. Maintenance crews had to establish inspection and coating maintenance schedules to address this issue. Despite these challenges, the overall performance of Marston mat in combat conditions exceeded expectations. Military commanders who had been skeptical of the portable runway concept became enthusiastic advocates after seeing how quickly airfields could be established and how well they performed. The ability to rapidly establish airbases was a significant factor in the success of the island-hopping campaign. It allowed American forces to project air power forward quickly, supporting each new amphibious assault with local air superiority.
Evolution and variance, adapting to new requirements. As experience with Marston mat accumulated, engineers recognized opportunities for improvement and adaptation. The original design was refined based on combat feedback, and specialized variants were developed for specific applications. This evolution demonstrated that the basic concept was sound and could be adapted to meet changing requirements. One significant development was the creation of lighter-weight mats for situations where the original mat was unnecessarily robust. These lighter variants used thinner steel and different hole patterns to achieve weight savings of 20% or more. While not suitable for heavy bomber operations, these lighter mats were perfectly adequate for fighter aircraft and liaison planes. The weight savings meant that transport aircraft could carry more mat sections per trip, and ground crews could handle them more easily. These light-duty mats found extensive use in forward areas where fighter strips needed to be established rapidly and where weight limitations on supply transport were severe. Conversely, heavier-duty mats were developed for use with the largest and heaviest aircraft. As B-29 Superfortresses entered service late in the war, their enormous weight, up to 70,000 pounds fully loaded, exceeded what standard Marston mat could safely handle for repeated operations. Engineers developed reinforced variants with thicker steel and modified connection systems that could support these behemoths. The trade-off was greater weight and more difficult handling, but for the strategic airfields from which B-29s operated, these sacrifices were acceptable. Specialized mat sections were created for specific applications. Turnaround pads, circular areas at runway ends where aircraft could turn around, required curved edge pieces and special corner sections. These pieces had to maintain the same strength as standard mats while accommodating nonlinear geometry. Taxiway intersections needed specialized crossing pieces, where two paths of mat came together at angles. Each of these special pieces had to be carefully designed to maintain structural integrity while serving its specific function.
The Army Air Forces and Navy also collaborated on developing specifications for carrier deck applications. While wooden carrier decks worked well for existing aircraft, the increasing weight of new designs meant that deck reinforcement would eventually be necessary. Marston mat technology offered a potential solution, though the marine environment and the specific stresses of carrier operations required significant modifications. These carrier variants never saw widespread use during World War II, but the development work laid groundwork for post-war aviation developments. In the European theater, Marston mat found different applications than in the Pacific. European terrain often allowed for better quality temporary airfields using compacted earth or existing infrastructure. But there were situations where rapid deployment capability was valuable. During the advance across France following D-Day, mobile airfields moved forward with ground forces, providing close air support. Marston mat enabled the construction of temporary fighter strips that could be established in days, used for weeks or months, and then either left behind or relocated as the front moved. One interesting adaptation involved combining Marston mat with other materials. In some locations, engineers would lay mat as a temporary surface, then pour concrete over or around it, essentially using the mat as permanent reinforcement within a concrete runway. This hybrid approach provided the rapid deployment benefits of mat while creating a more permanent installation for long-term use. The steel mat embedded in concrete provided excellent tensile reinforcement, improving the concrete's crack resistance.
Manufacturing innovation, the drive for efficiency. As demand for Marston mat increased throughout the war, manufacturers continually sought ways to improve production efficiency and reduce costs. These efforts led to significant innovations in manufacturing processes and quality control that had implications beyond just mat production. The scale of mat manufacturing, involving dozens of facilities producing millions of sections, created opportunities for process improvements that might not have been noticed in smaller production runs. One area of innovation was in the punching operation. The initial punch presses required frequent tooling changes and maintenance because the dies wore quickly from the repeated high-force stamping operations. Engineers developed improved die materials and coating technologies that extended die life significantly. They also refined the punching sequence, determining that punching the holes in a specific order reduced stress on the dies and produced cleaner edges on the holes. These improvements increased production rates and reduced scrap rates. The forming operations saw similar improvements. Early production often resulted in mats with slight variations in the hook and slot dimensions, leading to assembly difficulties in the field. Manufacturers implemented tighter process controls and improved measurement systems to catch dimensional errors earlier. They developed automated inspection systems using mechanical gauges that could quickly check critical dimensions without requiring extensive manual measurement. These quality improvements reduced field complaints and increased assembly efficiency. The anti-corrosion treatments evolved as well. Initial coating systems were adequate but not optimal. Some mats developed rust spots after extended tropical exposure. Chemical engineers experimented with various coating formulations, seeking the optimal balance of corrosion protection, application speed, and cost. They developed improved galvanizing processes that produced more uniform coating thickness. Paint formulations were refined to provide better adhesion and weather resistance. These coating improvements extended the service life of mats significantly, reducing the need for field maintenance and replacement. Bundling and shipping procedures were also optimized. Early shipments sometimes arrived with damaged mats because the bundling wasn't robust enough to survive rough handling during transport. Manufacturers developed improved bundling methods using better banding materials and protective edge pieces. They determined the optimal number of mats per bundle. Too few wasted shipping space and required more handling. Too many created bundles too heavy to move easily. The standardization of bundle sizes and the development of specialized handling equipment improved efficiency throughout the logistics chain.
Production capacity increased dramatically as the war progressed. Early production was limited by tooling availability and workforce training, but as manufacturers gained experience and invested in specialized equipment, output soared. By mid-1943, monthly production exceeded the most optimistic early estimates. This ramp-up in production was crucial because it coincided with the peak period of airfield construction across the Pacific Theater. The manufacturing effort also benefited from material science advances. Steel suppliers developed alloys specifically optimized for matte production, with characteristics tailored to the unique requirements of the application. These specialized steels offered better formability, improved corrosion resistance, and enhanced fatigue life compared to standard structural steel. The development of these materials demonstrated the close collaboration between material scientists, design engineers, and manufacturers, everyone working toward the common goal of improving the product. Beyond the war, legacy and lasting impact. When World War II ended in August 1945, the Pacific was dotted with hundreds of Marston mat airfields. Some of these installations were temporary and were quickly abandoned as military forces withdrew or consolidated, but many remained in use, and some continue to serve aviation purposes to this day, more than 75 years after their construction. The legacy of Marston mat extends far beyond its wartime service, influencing military engineering, civil aviation, and industrial design for decades. In the immediate post-war period, many Pacific islands transitioned their military airfields to civilian use. Islands that had been remote outposts suddenly had modern airfield infrastructure, and this enabled the development of regional air travel networks. Small airlines began serving routes between islands, connecting communities that had previously relied on slow and irregular boat service. The Marston mat runways, built for military necessity, became economic infrastructure that opened new possibilities for trade, tourism, and development. Some of the wartime airfields expanded into major airports. Henderson Field on Guadalcanal eventually became Honiara International Airport, the main airport for the Solomon Islands. Similar transitions occurred across the Pacific, with military infrastructure forming the foundation for civilian aviation. In many cases, the original Marston mat was eventually replaced with concrete or asphalt as traffic increased and resources became available. But the layout, orientation, and basic design of these airports still reflect their wartime origins. The technology itself continued to evolve in the post-war era. The U.S. military recognized that the rapid airfield construction capability that Marston mat provided remained strategically valuable even in peacetime. Engineers developed improved versions with better materials, optimized designs, and enhanced durability. These post-war variants saw use in Korea during the 1950s, where the ability to rapidly establish forward airfields proved crucial once again. The basic concept, portable, interlocking mat sections that could be quickly assembled, remained sound, but the execution improved with each generation. The Vietnam War saw extensive use of mat technology in Southeast Asia. American forces constructed numerous airfields in remote areas using systems descended from Marston mat. The jungle conditions in Vietnam were similar to the Pacific Islands 2 decades ago, and the same engineering principles applied. By this time, helicopter operations had become crucial, and specialized mat variants were developed for helicopter landing pads and forward arming and refueling points. The mats had to withstand the different stress patterns that helicopters created: concentrated rotor downwash, hot exhaust, and hover loads rather than rolling loads. Beyond military applications, Marston mat influenced civil engineering in unexpected ways. The concept of modular, prefabricated infrastructure that could be rapidly deployed found applications in disaster relief and remote area development. After earthquakes, hurricanes, or other disasters that damaged airports, temporary runways could be established quickly to facilitate relief operations. In areas where permanent infrastructure wasn't economically justified, temporary mat installations provided adequate capability. Mining operations in remote locations used mat technology for airstrips serving their camps. Exploration companies working in jungles or Arctic regions used mats to create helicopter pads and small airfields. The offshore oil industry adopted related technologies for helicopter landing platforms on oil rigs. While the specific designs differed from Marston mat, the underlying principles, prefabricated sections, efficient weight-to-strength ratio, corrosion resistance, and modular assembly, came directly from the wartime mat development. The engineers designing offshore platforms studied Marston mat as they developed their own solutions to similar problems. Even modern military engineering still references Marston mat when developing portable airfield systems. Current systems use advanced materials like aluminum honeycomb composites, fiber-reinforced polymers, and specialized alloys that didn't exist during World War II. But they're solving the same fundamental problem: how to create strong, lightweight, rapidly deployable runway surfaces. The AM2 matting system used by the U.S. military today is a direct descendant of Marston mat, incorporating 70 years of improvements while maintaining the core concept. The influence extended into architectural and structural engineering as well. The use of perforated metal for structural applications became more common after engineers saw how effectively the Marston mat design distributed loads while minimizing weight. Perforated metal flooring, stair treads, and walkways in industrial facilities often use design principles derived from mat technology. The interlocking connection systems developed for mat assembly influenced the design of modular building systems and temporary structures.
The human element. Stories from the field. Behind the statistics, engineering specifications, and strategic implications, Marston mat's story is ultimately about the people who designed it, manufactured it, transported it, assembled it, and used it. The engineers who developed the system worked under enormous pressure, knowing that lives depended on their success. They labored through countless failures and setbacks, gradually refining the design through persistence and ingenuity. Many of these engineers were civilian contractors working for the Corps of Engineers, men who had been designing bridges, dams, and buildings in peacetime, but who turned their skills to war work when called upon. The Seabees who constructed the airfields came from diverse backgrounds. Before the war, they had been carpenters, plumbers, electricians, heavy equipment operators, and construction workers. The military trained them in the specific techniques needed for combat construction, but their civilian experience provided the practical skills foundation. These men worked in conditions that were often appalling: tropical heat and humidity, torrential rain, clouds of mosquitoes, tropical diseases, and the constant threat of enemy attack. They worked long shifts with inadequate rest, pushing themselves to exhaustion because they knew that aircraft crews were depending on them. There are countless stories of heroic effort and determination. At Iwo Jima, CB battalions began constructing airfields while the battle for the island was still raging. They worked under artillery fire and sniper attacks, suffering casualties while continuing their construction work. The airfields they built allowed damaged B-29s returning from bombing raids on Japan to make emergency landings, saving aircraft and crews that would otherwise have been lost. The first emergency landing occurred while construction crews were still working on portions of the runway. They stopped their work, moved their equipment aside to clear the runway, and then resumed construction after the aircraft was safely down. Personal accounts from Seabees described the physical demands of the work. Handling 70-pound mat sections in tropical heat was exhausting. Men would work until they could barely stand, take a short break, and then return to work. Dehydration and heat exhaustion were constant threats. The work was also monotonous, laying mat section after mat section, hour after hour, the same repetitive motions thousands of times. But the crews found ways to maintain morale. They competed with other units to see who could lay mat fastest. They took pride in their work, knowing that every section they laid brought the airfield closer to completion and brought victory closer.
The aircraft mechanics and pilots who used the airfields developed their own relationships with the mat runways. Pilots learned the visual characteristics of mat runways, the distinctive rectangular pattern, the way water drained through the perforations, the particular sound and feel of landing on mats. Some pilots preferred mat runways to dirt or coral strips because they provided more consistent surface characteristics and better traction. Others were initially nervous about the perforated surface, concerned about tire damage or unusual handling characteristics, but experience taught them that properly laid mat was safe and reliable. There are stories of makeshift repairs and field innovations. When mat sections were damaged and replacements weren't immediately available, maintenance crews improvised. They welded patches onto damaged mats, sometimes using pieces cut from other damaged sections. They developed techniques for straightening bent mats using jacks and bars. They learned which types of damage could be safely ignored and which required immediate attention. This practical knowledge, accumulated through experience, often wasn't written down in official manuals, but was passed from one crew to another through word of mouth.
Technical Deep Dive: The Mathematics of Mat Design. For those interested in the engineering details, the design of Marston mat involved sophisticated mathematical analysis and material science. The engineers had to solve complex problems in structural mechanics, dealing with dynamic loads, fatigue analysis, and material behavior under extreme conditions. While the final product appeared simple, just a perforated steel plate with some hooks on the edges, the design process involved calculations and analyses that pushed the limits of engineering knowledge in the 1940s. The fundamental challenge was determining the optimal thickness of steel and the pattern of perforations that would provide adequate strength while minimizing weight. Engineers used beam theory and plate theory from structural mechanics to model how loads would distribute through the mat structure. They had to account for various loading conditions: static loads from parked aircraft, dynamic loads from landing impacts, fatigue from repeated loading cycles, and thermal stresses from temperature changes. The perforations created a complex stress distribution pattern. Around each hole, stress concentrations occurred. The forces flowing through the steel had to divert around the holes, creating higher local stresses near the hole edges. Engineers used photoelastic analysis, a technique where transparent models are viewed under polarized light to visualize stress patterns, to study these stress concentrations. They discovered that the elongated hole shape helped reduce peak stresses compared to circular holes, and that proper spacing between holes was critical to prevent stress concentrations from adjacent holes from interacting and creating failure points. The interlocking mechanism required careful design to ensure that it could transmit shear forces between adjacent mats without failing. When an aircraft wheel rolled across the joint between two mats, it created shear forces trying to slide one mat relative to the other. The hooks and slots had to be strong enough to resist these forces and stiff enough to prevent excessive movement that would create bumps or gaps in the runway surface. Engineers performed detailed stress analysis on the hook geometry, determining optimal hook depth, thickness, and angle to maximize strength while maintaining ease of assembly. Fatigue analysis was particularly important because the mats would experience repeated loading cycles, thousands or even tens of thousands of aircraft operations over their service life. Each landing created a stress cycle, and even though the stress might be well below the steel's ultimate strength, repeated cycling could cause fatigue cracks to initiate and grow. Engineers used SN curves, plots of stress amplitude versus number of cycles to failure, to predict the fatigue life of the mats. They designed the mats to have adequate fatigue strength for the expected number of operations, with safety factors to account for uncertainties in usage and material properties. The connection between individual mats created an interesting structural problem. The runway wasn't a continuous plate, but rather an assembly of discrete sections connected together.
Engineers had to analyze how loads would transfer across these connections and how the discontinuities would affect overall structural behavior. They used concepts from the theory of composite structures, treating the assembled runway as a kind of mechanical composite where the connection system played a role analogous to the matrix in a fiber-reinforced composite material. Thermal analysis required calculating how much the mats would expand when heated by tropical sun and ensuring that the connection system could accommodate this expansion without causing buckling or connection failure. Steel's coefficient of thermal expansion meant that a 10-foot mat section could expand by nearly 1/10 of an inch with a 50-degree temperature change. Multiplied across a 3,000-foot runway, this added up to significant overall expansion. The connection system's small amount of free play allowed each mat to expand slightly without transmitting stress to adjacent mats, preventing thermal buckling. The drainage characteristics were also analyzed quantitatively. Engineers calculated the flow rate of water through the perforations using principles from fluid dynamics. They needed to ensure that even in heavy tropical downpours, water would drain through the mats faster than it accumulated on the surface. This required knowing the rainfall intensity, the runway drainage slope, and the flow characteristics through the perforations. The calculation showed that the perforation pattern provided more than adequate drainage capacity for any realistic rainfall rate.
Comparative analysis, Marston mat versus alternatives. To fully appreciate Marston mat's achievements, it's useful to compare it with alternative approaches to temporary airfield construction. Several competing systems existed during World War II, and examining their relative strengths and weaknesses provides insight into why Marston mat became the preferred solution for many applications. The most obvious alternative was simply compacted earth or coral. When conditions were right, firm soil, good drainage, dry climate, a graded and compacted earth runway could work adequately for lighter aircraft. The advantages were clear: no manufactured materials required, no shipping burden, construction used only local resources. But earth runways had severe limitations. They deteriorated rapidly in wet conditions, turning into impassable mud. They required constant maintenance and regrading. Heavy aircraft would create ruts and depressions that could damage landing gear or even cause crashes. Dust in dry conditions created visibility problems and engine wear. For high-tempo operations with heavy aircraft, earth runways simply weren't adequate. Concrete offered permanence and durability, but required massive amounts of materials, heavy construction equipment, long curing times, and skilled labor. A typical concrete runway required thousands of cubic yards of concrete, which meant shipping cement, sand, aggregate, and water to the construction site, or establishing concrete production facilities nearby. The concrete had to be mixed, placed, finished, and allowed to cure for days or weeks before it could handle aircraft loads. In combat situations where time was critical, concrete wasn't practical for initial airfield construction, though it was sometimes used to improve temporary installations for long-term use. Wooden planking was tried in various configurations. Wood had the advantage of being available locally in jungle environments, and it was relatively easy to work with using hand tools. Some experimental wooden runways were built, especially for lighter aircraft and in remote locations where Marston mat wasn't feasible. But wood had fatal weaknesses in tropical environments. It rotted quickly in humidity. Termites and other insects attacked it. It splintered and cracked under repeated stress. Water made it slippery and weak. Fire was a constant hazard. A crashed aircraft could ignite a wooden runway, destroying the entire installation. Overall, wood wasn't suitable for high-capacity, long-duration operations. The British developed various steel mat systems, including Sommerfeld track and other designs. These systems had similar concepts to Marston mat, but different implementations. Some British mats used mesh or grid patterns rather than perforated plates. Others used different connection mechanisms or different materials.
Comparative testing showed that Marston mat generally offered better strength-to-weight ratios and easier field assembly than most competing designs, though some British systems had advantages in specific applications. Aluminum matting was explored as a lighter alternative. Aluminum's lower density meant that sections could be lighter for the same strength, or the same weight sections could be larger, potentially speeding assembly. But aluminum had significant drawbacks. It was expensive and in short supply. Aluminum was needed for aircraft production, and allocating it to runway construction competed with aircraft manufacturing. Aluminum was also softer than steel and more prone to damage. It had lower fatigue strength, potentially limiting runway lifespan. While aluminum mats saw limited use in some applications, steel remained the preferred material for most installations. Various hybrid approaches were tried, combining materials or techniques. Some installations used mat for the main runway, but earth or gravel for taxiways and parking areas, economizing on mat usage. Others used mat as temporary surfacing while concrete was being prepared, and then replaced sections with concrete over time. These hybrid approaches often made economic sense, using each material where its advantages were greatest. The comparison ultimately showed that no single solution was optimal for all situations. Marston mat's great advantage was its versatility. It worked acceptably well across a very wide range of conditions and requirements. While it might not be the absolute best choice for any specific narrow scenario, it was good enough for most situations, and its standardization meant that crews became skilled at working with it. Logistics systems were optimized for it, and supply pipelines were established for it. This universality and standardization often outweighed any technical advantages that specialized alternatives might offer.
Environmental and long-term impacts. The environmental legacy of Marston mat installations is complex and worth examining. Thousands of tons of steel were shipped to remote Pacific islands and assembled into airfields. When these airfields were abandoned, what happened to all that material? In some cases, mat sections were recovered and reused elsewhere or shipped back for recycling. But in many instances, especially on remote islands or where operational priorities demanded rapid movement, the mats were simply left in place. Decades later, some of these abandoned mat sections remain visible, now overgrown with jungle vegetation, but still recognizable. They've become historical artifacts, physical evidence of the war that swept across the Pacific. On some islands, local populations have found uses for the old mat sections, as building materials, as fencing, as structural elements in local construction. The durability that made Marston mat effective as runway surfacing also means it persists in the environment for decades. From an ecological perspective, the presence of these steel mats has had mixed effects. The mats themselves don't introduce toxic chemicals or hazardous materials into the environment. They're just steel, slowly rusting away over decades. But they do represent an intrusion of industrial infrastructure into what were often pristine or lightly inhabited islands. The airfield construction process involved clearing vegetation, moving earth, and fundamentally altering local landscapes. Some of these alterations persisted long after military operations ended. On the positive side, some of the environmental modifications actually created new habitats. The cleared areas and drainage ditches associated with airfields sometimes became wetlands or grasslands that supported different species than the original jungle. In some cases, these new habitats increased local biodiversity by creating habitat variety. The runways themselves, when abandoned, sometimes became open areas in otherwise dense jungle, and these openings allowed sunlight penetration that enabled different plant communities to establish. The long-term material fate of the mats is slow oxidation. Steel exposed to tropical conditions will eventually rust away completely, though the process takes many decades. The corrosion-resistant coatings applied during manufacture slow this process significantly,
but they don't prevent it indefinitely. As the mats corrode, the iron returns to iron oxide compounds, essentially rust, which are naturally occurring and non-toxic. From a long-term perspective, the mats are gradually returning to the environment in forms that aren't particularly harmful. Contemporary efforts at some historical sites have focused on preservation rather than removal. Several former airfields in the Pacific have been designated as historical sites or memorials. Organizations dedicated to preserving World War II history have worked to stabilize remaining mat sections, document the installations, and interpret them for visitors. These sites provide educational opportunities, allowing people to see and understand the engineering achievements and historical significance of these installations. The question of whether the abandoned mats should be removed has been debated. Environmental advocates sometimes argue for removal to restore sites to more natural conditions. Historical preservationists want to maintain them as artifacts. Economic considerations also play a role. The cost of removing thousands of tons of mat from remote islands would be substantial, and the scrap value of heavily corroded steel is minimal. Most abandoned installations have simply been left in place, slowly deteriorating, their historical significance fading as vegetation reclaims the sites.
Modern military engineers still study Marston mat when developing contemporary rapid airfield construction systems. The lessons learned from mat design, deployment, and use remain relevant even as materials and technologies have advanced dramatically. Current systems benefit from 8 decades of progress in materials science, manufacturing technology, and engineering analysis, but they're still solving fundamentally similar problems. Modern portable runway systems use advanced materials that would have seemed like science fiction to the World War II engineers. Aluminum honeycomb panels sandwich a lightweight honeycomb core between aluminum face sheets, creating incredibly stiff and light structures. Fiber-reinforced polymer composites offer excellent strength-to-weight ratios and complete corrosion immunity. Specialized aluminum alloys provide better performance than the steel used in original Marston mat while weighing significantly less. These materials allow modern systems to be lighter, stronger, and more durable than their predecessors. Manufacturing technology has also advanced enormously. Computer-aided design allows engineers to optimize every detail of mat geometry using sophisticated finite element analysis. Automated manufacturing processes produce parts with tolerances that would have been impossible to achieve with 1940s technology. Quality control systems using laser measurement and computer vision catch defects that human inspectors might miss. These advances result in more consistent products with better performance. Despite these technological advantages, modern systems still face many of the same fundamental challenges that Marston mat addressed. Weight remains critical. Mats must be light enough to transport efficiently and handle manually when necessary. Strength is still paramount. Modern aircraft are even heavier than World War II bombers, and their landing gear loads are correspondingly greater. The connection system must still allow rapid assembly by personnel working in difficult conditions. Durability in harsh environments is still essential. The solutions have evolved, but the problems remain recognizable. The U.S. military's current AM2 matting system, introduced in the 1960s and still in use today, shows clear lineage from Marston mat. It uses aluminum instead of steel, has a different perforation pattern optimized using computer analysis, and features improved connection mechanisms. But the basic concept, interlocking perforated panels that assemble into a continuous runway surface, is unchanged. The AM2 system has been used extensively in recent conflicts in Iraq and Afghanistan, proving that the portable mat concept remains relevant in 21st century warfare. Modern engineers also benefit from decades of operational experience that guides their designs. They know from extensive field use which aspects of portable mat systems work well and which cause problems.
They understand the maintenance issues that arise, the failure modes that occur, and the operational limitations that users encounter. This accumulated knowledge, much of it originally gained from Marston mat experience, informs every aspect of contemporary system design. The logistics and deployment procedures developed for Marston mat also continue to influence military operations. The U.S. military maintains specialized units trained in rapid airfield construction, direct descendants of the World War II CB battalions. These units practice deployment procedures, maintain equipment stockpiles, and develop doctrine for various scenarios. When military operations require forward airfield establishment, these units execute procedures that would be recognizable to World War II engineers, though executed with modern equipment and materials.
The psychological impact. Engineering under pressure. Beyond the technical and operational aspects, it's worth reflecting on the psychological dimension of the Marston mat story. The engineers who designed it worked under enormous pressure. They knew that the outcome of battles, the success of campaigns, and ultimately the course of the war might depend on their success. This wasn't abstract knowledge. Engineers received regular updates on the Pacific campaign's progress, and they understood exactly how critical airfield construction capability was to military operations. This pressure could have been paralyzing, but instead it seems to have been motivating. The engineering team worked with remarkable focus and intensity. They ran test after test, analyzed failure after failure, and refined their design through countless iterations without becoming discouraged. When one approach didn't work, they immediately tried another. When manufacturing problems arose, they worked with production engineers to solve them. This persistence in the face of repeated setbacks demonstrates psychological resilience that was as important as technical skill. The CB construction crews also operated under intense psychological pressure. They worked in combat zones, often under enemy fire, knowing that their lives were in danger. But they also knew that their work directly protected other servicemen, the pilots who would use the airfields they built. This sense of purpose, the knowledge that their exhausting and dangerous work served a vital mission, helped sustain morale through incredibly difficult conditions. There are accounts of construction crews working through exhaustion, pushing themselves far beyond what they thought their limits were. Men would work until they collapsed, rest briefly, and then return to work. This extraordinary effort wasn't forced through harsh discipline. It came from internal motivation, from the understanding that finishing the airfield quickly could mean the difference between victory and defeat in an ongoing battle. This psychological dimension of the Marston mat story, the human determination and commitment that made the technical achievement possible, is as important as the engineering itself. For the pilots and aircraft crews who used mat runways, there was a psychological comfort in knowing how the runways were built. Many pilots visited airfields under construction, watching CBs lay mat sections. They could see the care that went into the work, the quality of the materials, and the skill of the construction crews. This knowledge built confidence in the runway surface and reduced anxiety about landing on what might otherwise seem like a questionable temporary strip. Trust in the engineering and construction quality allowed pilots to focus on their missions rather than worrying about whether the runway would hold up.
Economic considerations. The cost of rapid deployment. The economics of Marston mat production and deployment are fascinating and illustrate the massive industrial effort behind military operations. During the peak production years of 1943 and 1944, the United States was producing Marston mat at a rate that consumed thousands of tons of steel monthly. In today's terms, the total investment in mat production, including material costs, manufacturing facility construction, tooling development, quality control systems, and logistics infrastructure, would amount to billions of dollars. This enormous expenditure was justified by the strategic value that rapid airfield construction provided.
Military planners conducted cost-benefit analyses comparing different approaches to airfield construction. They calculated that even though Marston mat was expensive to produce and ship, it was far more cost-effective than the alternatives when all factors were considered. A mat runway could be operational in days compared to months for concrete. This time savings meant that air operations could begin sooner, providing air support and air superiority that protected ground forces and naval vessels. The lives saved and missions accomplished because of this time advantage far outweighed the material costs of the mat system. The economic calculations also considered opportunity costs. If airfields took months to build, then construction equipment, engineer battalions, and cargo shipping capacity were tied up for those months and unavailable for other uses. Fast construction with Marston mat freed these resources for other purposes. The construction crews could move on to the next project, the cargo ships could return for other supplies, and the heavy equipment could be deployed elsewhere. This resource velocity, the ability to quickly complete projects and move resources to new applications, provided economic leverage that simplified analyses focusing only on direct material costs would miss. The post-war economic impact was also significant. The industrial capacity built for mat production couldn't simply be shut down overnight. Factories, equipment, and trained workers represented major investments. Some facilities transitioned to other steel products, applying the manufacturing expertise developed for mats to new applications. Workers who had gained specialized skills in mat production brought that knowledge to post-war industries. The economic ripple effects of wartime mat production extended for years beyond the war's end. For the Pacific Islands themselves, the airfields represented a form of economic development, even though that wasn't their original purpose. Islands that had minimal infrastructure suddenly had modern airfields capable of supporting regional aviation. This infrastructure enabled post-war economic development, tourism, and trade that wouldn't have been possible otherwise. While this development brought its own challenges and disruptions to traditional island societies, it also created new opportunities and connections to the broader world.
The archival record documenting the technology. The documentary evidence surrounding Marston mat development and use provides fascinating insights into both the technology itself and the historical context in which it was developed. The National Archives holds extensive records from the Corps of Engineers, including design drawings, test reports, manufacturing specifications, deployment records, and after-action reports from construction battalions. These documents tell a detailed story of technological development under wartime pressure. The design drawings are particularly revealing. Early concept sketches show the evolution of ideas, with handwritten notes and calculations in the margins where engineers worked through problems. The drawings show features that were considered but ultimately rejected, design elements that changed as testing revealed problems, and the gradual refinement toward the final configuration. Studying these drawings provides insight into the engineering design process and the iterative nature of development. Test reports document the extensive evaluation program that validated the mat design. These reports include detailed data tables, graphs showing load deflection curves, photographs of test setups and failure modes, and engineers' observations about performance characteristics. The reports reveal how thoroughly the system was tested and how methodically engineers analyzed the results. They also show the high professional standards that governed military engineering during this period. These weren't casual tests, but rigorous scientific investigations. Manufacturing specifications are precisely detailed, reflecting the need for consistent quality across multiple manufacturers. The specifications define material properties, dimensional tolerances, coding requirements, and acceptance testing procedures. They're written in careful technical language that leaves no room for ambiguity. These documents enabled the distributed manufacturing system to work effectively. Any qualified manufacturer could produce mats to the same specification, ensuring interoperability. Deployment records from CB battalions provide operational perspectives on how the mats actually performed in combat conditions. These records include construction schedules showing how quickly airfields were built, maintenance logs documenting problems and repairs, usage statistics tracking the number of aircraft operations, and damage reports from enemy action.
Personal accounts from construction personnel add human detail to the statistical records, describing working conditions, challenges encountered, and solutions improvised in the field. Photographic archives contain thousands of images documenting every aspect of Marston Matt's story. Photographs show manufacturing facilities with workers operating punch presses and forming machines. They depict cargo ships loaded with bundled mats, landing operations on Pacific beaches, construction crews laying sections, and aircraft operating from completed airfields. These images provide visual documentation that complements the written records and helps modern viewers understand the technology and its context.
Conclusion: Engineering excellence in crisis. The story of Marston Matt represents engineering excellence achieved under the intense pressure of wartime necessity. When the challenge arose, build airfields in jungles within 48 hours, it seemed impossible. Conventional approaches to runway construction simply couldn't meet the requirement. Success required innovative thinking, rapid development, rigorous testing, massive industrial production, complex logistics, and skilled field execution. That all of these elements came together successfully in wartime conditions in the span of just a few years stands as a remarkable achievement. The engineers who designed Marston Matt solved a genuinely difficult problem. They balanced competing requirements that seemed mutually exclusive: strength and lightweight, quick assembly and secure connections, durability and low cost. They used clever design to maximize structural efficiency. They developed manufacturing processes that could produce millions of sections with consistent quality. They created a complete system, not just a product. Mats, connections, tools, procedures, and training all working together. The Seabees and Army engineers who deployed and used the mats demonstrated that technological excellence means little without skilled execution. They adapted to local conditions, improvised solutions to unexpected problems, and worked with determination under incredibly difficult circumstances. They turned engineering specifications into functional airfields that serve their purpose brilliantly. The ultimate validation of the Marston Matt system is simple. It worked. Airfields were built in jungles within days. Aircraft operated from these airfields safely and effectively. The ability to rapidly establish airbases contributed meaningfully to Allied victory in the Pacific. The technology was so successful that it influenced military engineering for decades afterward and remains relevant today. But perhaps the deepest lesson from the Marston Matt story isn't technical. It's about what humans can achieve when urgency, purpose, and skill combined. The engineers, manufacturers, logistics personnel, and construction crews who made Marston Matt successful weren't working in comfortable laboratories or ideal conditions. They faced time pressure, resource constraints, dangerous working environments, and the stress of knowing that lives depended on their success. Yet they performed brilliantly. This story reminds us that engineering isn't just about calculations and materials. It's about solving real problems for real people in real situations. The best engineering responds to genuine needs with practical solutions. Marston Matt met that standard completely. It was exactly what was needed, delivered when it was needed, and it worked as intended. That's engineering excellence. When we look back at World War II, we often focus on the dramatic battles, the famous generals, the strategic decisions. These are important, but they were made possible by countless acts of technical competence and determination. The engineers who designed Marston Matt, the workers who manufactured it, the personnel who transported it across oceans, and the Seabees who assembled it in combat zones all contributed to victory. Their names are mostly forgotten, but their achievement endures. 75 years later, some of their work remains visible on remote Pacific islands, steel mats slowly rusting away under jungle growth. These physical remnants are monuments to innovation, perseverance, and skill. They remind us that when faced with impossible challenges, determined people equipped with knowledge and driven by purpose can accomplish remarkable things. The story of how engineers designed Marston Matts to build airfields and jungles within 48 hours
is ultimately a story about human capability, our ability to solve problems, overcome obstacles, and achieve goals that initially seem beyond reach. That lesson remains relevant today, whatever challenges we face.